All right. Well,
I don't
welcome
know.
everyone. Welcome everyone to our capital area.net user group. To kick us off, we have Clark Sell from that conference, who's going to share a little bit about that and some other details. So take it away, Clark.
Thank you, Labrina, and thank you, Lee, both of you, for inviting me to be here. Just like everybody who's come, you know, I want to extend a bit of gratitude to not only you for showing up, but you guys for hosting, and Jason for speaking. You know, I think that this is, if I go back, you know, I don't know, 15, 20 years, this was pretty critical to my existence on this planet and kind of learning how to level up. So I say that because that life led me to starting something called That Conference. And as you know, the last 3 years have been a drag for people, especially trying to get out and get community. And because of that, I'm just on a mission to try to make sure that nationally and globally, we all connect or reconnect, depending upon how you want to look at it. As Labrina said, I am the founder of I guess an organization called That Conference. We run 2 in-person conferences, one in January in Texas and the other in July in, nope, I said that wrong. Texas in January and in Wisconsin in July. And then we do stuff online all the time. We have something called Open Spaces at the conference, and we used the pandemic to bring that online for everybody. So if you want to think Meetup meets Zoom or Teams meets Stack Overflow, we're trying to reimagine kind of how we interact online together as a community overall. So that being said, we're always looking for people to come to the conference. We're always looking for speakers. We're happy to help mentor people. So if you're interested in ever doing that, even if you're not even want to speak at that conference, you want to speak somewhere else and you just want some tips, God bless, I'd be happy to help you out. So if you want to be involved in some way, reach out. You can find me at hello@thatconference.com or at that conference anywhere. If you want to learn more about that conference, you can go to thatconference.com. And that's me. Brandon, anything you want to, you're pretty deep in this as well.
Deep in this or deeper that?
Deep in that.
Deep in that. Yeah. I'll add a couple things as well. So, hey, everybody, Brandon Martinez, as already mentioned, you know, Labrina and I work together, which helped make this connection. So thank you, Labrina. I've been involved with that for like the last, I don't know, 7 years, whether it's attending or helping out in one way or another. Anywhere from photography to social to really whatever Clark needs. And it's been just an excellent experience. So as someone that was part of the community through things like user groups and being able to meet people in person or virtually, and seeing a community grow beyond just my local user groups into something a little more regional, and now with us adding in Texas at a national type level, it's really great to be able to connect. And I think that provides an experience unlike a lot of other conferences that I've been to or been involved in. It just adds this level of community that feels almost like, and I know this word gets overused a lot, but like a family of developers, geeks, nerds, and really just brings together people in a different fashion outside of work, outside of just regular user groups. So would love to see anyone and everyone there and see you in person.
Yeah. And I'll just add to, because I got the opportunity to go to that conference this summer in Wisconsin. And the one thing that I love, in addition to all the great like technical geek community, is that it is about family. So you can bring your kids. I brought my niece and my cousin, who are 7 and 17, so completely different ends of the like kid spectrum. And I thought it was going to be like, I thought I was going to have to spend my entire time because it's at the Kalahari Resort. So they mainly came because I promised them water slides, but and I thought I was going to have to like negotiate things to like, you know, spend time at the conference and then like, oh, if you like spend some time with me here, we'll go to the water slides. But it actually like they actually sort of started forgetting about the water slides and enjoyed the content there. And I could like, we started the morning like, hey, come in, let's go. Cause they have this like really cool, like open room with lots of activities for kids. And I was like, hey, like come in, like spend 5 minutes with me. And they're like, okay, but 5 minutes exactly. And they were going to the pool. And then like 5 minutes turned into 15 to 20, like, and we were there for like hours in the room, like totally unprompted. So I definitely can attest to the family environment, and it was really, really, really a good time. So definitely appreciate it. I definitely am a fan of that conference. So.
Well, I appreciate the Labrina, and I appreciate you giving us the time to remind folks that there's stuff going on. And, you know, again, everybody who came to this, you know, seriously shout out for stepping out and trying to level up, and folks like Jason who speak all over the place and do that. I think it's, all these pieces matter when it comes to community, and all these pieces, you know, help us all grow. And that's what we're really passionate about. So, I don't want to take up a bunch of time from Jason. Seriously, if you're interested in anything related to that, feel free to reach out. Check us out on thatconference.com. If you want a little discount on a ticket, because it's easy to fly to Texas versus where we are in Wisconsin, you can use a discount code called Clark. They give you 5% off your order. You want to speak? Wisconsin will open up January 1st. And yeah, just kick some ass.
Thank you guys so much.
All right, thank you all both. So Jason, are you ready?
Yes, I am.
I'm gonna spotlight you. Do. Like the things keep moving around, so I couldn't. Things keep moving around in Teams. All right, cool. All right, so
Okay.
without further ado, welcome our speaker, Jason, who's going to talk big numbers.
Yes, I am. So let me, before I forget, we're going to say this and then that and share. And it's good because I can actually see myself, like what Clark was saying, the inception part where I can see on the screen. Before I actually start to talk, just two things I want to mention, and to reiterate what Clark was saying about that conference. I've been involved with it in terms of being a speaker for a long time. I don't remember exactly the first one I did, but the first that conference I was at, my kids were probably like 5 and 3 or 6 and 4 or something like that. They were really young, and they were doing the slides and the water park and stuff like that. This year, my kids are now a senior and a sophomore in high school, and you know they kind of had their own things, and so it was just my wife and I decided to get a night, you know, at a hotel in a resort where we didn't have to have kids around. So, but I've been to that conference a lot. It was in Texas last year, and it's a really good conference. So if you see this either tonight because you're at the user group or you're watching the recording later, it's definitely a conference I would check out. The other thing I want to mention about the user group is I'm going to drag this over, and I realize I've spoken at this group twice before. In fact, way back in 1999, I did this talk at the group called The Limits of Visual Basic. And I don't think it was in that same room, but it was somewhere in the DC area. And like, while I'm here tonight at home in the Twin Cities, you know, probably would have been an adventure getting there tonight or today with the weather we've had with all the snow. The fact that I can do this online is a good thing, but I definitely remember this group. it was actually a very fun time doing the talk and hanging out with people afterwards, you know, and that's the fun thing about doing these kind of community events is not just presenting, but hearing what other people have to say. I really do enjoy that. So while we can't go to a bar afterwards, you know, the still having this time to have these kind of conversations is a good thing. And what I have in my drink here, you know, you can just leave to your imagination. So let me get to my actual slides here and do that. Now, by the way, you're going to see me kind of look over here at times. It's because I have my other monitor here and I do have the chat up, but when I'm doing my presentation, it has the notes thing here and then the actual presentation here. So if you do have a question, and I was going to mention this on the next slide, but if you do have a question, especially in this virtual presentation world, just yell at me. Just, you know, you can put something in chat, but I might not see it. So don't feel bad at all about just, you know, coming out the mic or just yelling in the room or whatever and saying, hey, Jason, I got a question. And I'd be more than happy to just stop and, you know, let you ask it and I'll try to answer it as best as I can. Yep. So again, the topic is big numbers. Again, my name is Jason Bock. My title technically is developer advocate. I do work at Rocket Mortgage. That title, though, will be changing. I was in a DevRel group that all of that stuff got disbanded at the end of last year. But fortunately, I landed on a team called Rocket Libraries. We build packages, components, frameworks that other engineers use to build applications for Rocket Mortgage. So that's actually worked out really well. They highly encourage me to keep doing this type of stuff. So it's turned out to be a really good situation. It's just my title doesn't really match what I'm doing anymore. So that will change in the very near future. But, you know, big companies, sometimes that change takes a little bit of time. So, but yeah, I've been there for a couple of years now. Before that, I did a lot of consulting work for about 23 years of my life. So that's a little bit of history about myself. You can find out more information about me if you'd like. You can check out these links. If something comes up afterwards, if you got a question, just shoot me an email, jason.r.bock@outlook.com, and I would be happy to answer it that way. And hide that so that gets out of the way. All right. So there are some repositories that if you want to check out, you can feel free and do so. I'm not going to be going through all these tonight, but you know, feel free to take a look at the code. I do keep a PDF version of my slides up at that last repository. So this presentation, I'm going to point it out. There's one or two slides I had to change right before I joined online because I found out some new things. And of course, any presenter will tell you, don't do that. That's a big mistake. But I just changed the picture, so no big deal. But I will make sure that the most recent, latest, and greatest copy is up there for this talk. And I highly recommend that you do get the PDF because in the notes section, I try to have links to things that are relevant to that slide. In the last slide, I have a whole bunch of references to other things, so you can take a look at that stuff later. Take a look at that stuff later if you'd like. So I'm going to talk a little bit about the relevance of this talk. Why am I doing it? What's the point of it? What's the inspiration of it? We're going to talk a little bit as well about representation of numbers, and that's where the demos are going to come in and why it matters, what kind of number types you're using, especially if you're trying to do stuff with bigger calculations. We're going to go kind of off the deep end at the end, talking about some numbers that are just, when I talk about big, you can't even describe how big they are. They're absolutely massive. And then we'll end it with a call to action. So relevance, why am I doing this talk? What's the point of it? Why did I come up with all this material? In part, and I was mentioning this before I started, but this is kind of meant to be a fun talk. Though if you have kids, you may be looking at this and absolutely being terrified because you're like, oh my God, what a mess that's going to be. But it really is meant to be just fun. There's some talks that I do that are, I think, a little bit more relatable in terms of, hey, what's new in C#, or what's the latest stuff that's in .NET, or building source generators, or doing code analysis, stuff that you could potentially take from listening and use it in your day-to-day job. This one, I know Lee's really excited about it, but this one arguably may not be as relevant from that perspective. Though I hope there are things that I talk about tonight that perk your interest. You may not use them when you go back to your job tomorrow, but that may pique that interest, that insight, that curiosity to just look at stuff. And I find that in life just to be so much fun. I mean, that's what makes life interesting, is just to dive into things that you have no idea about. And even though you may not become an expert, and I don't claim to be an expert on any of this stuff, I've always been fascinated about these things. It gets you into topics that may actually have some relevance in other things later on in your career. You never know. Okay, but this is primarily just because this is fun, and along with that, like, this is all fun, and this may sound weird, but I remember as a kid, speaking about having a picture of kids just like making a complete mess. I remember as a kid, I wasn't making a complete mess at the time, but finding out about big numbers. I remember finding out about this number that was called a Google. Like, when, I admit I'm a geek, I'm a nerd. I love math, even though I don't think I'm highly skilled at it, but I've always liked math, astronomy, that type of stuff. And early on in my life, I started getting fascinated about numbers like thousands and hundreds of thousands and millions and billions, and you can just keep adding on to it. And then I found out about this thing called a Google, which is 10 to 100. Now, if you don't know what that notation is there, because I'm going to have some math in this talk. I don't make this a very math heavy talk, but there are some things I'm going to show. So that is, if you do have a question on it, again, feel free to ask. I've done this talk before, and somebody did say, I don't understand what this notation is. And maybe you don't, you just have never seen it before. All this is saying is that it's basically 10 raised to the 100. In other words, you multiply 10 to itself 100 times. Okay. And so you got basically one with 100 zeros after it. And that's a really big number. Okay. But as you start looking at numbers, you quickly realize you can just put another number at the end of it and just keep going and going. And when does it end? There's a couple of other books that, as I was growing up, that I read and I stumbled across that really opened my perception and like what I viewed of numbers and how they were relevant in the world that we live in and the universe we live in. The one on the left there from Isaac Asimov, it was called The Collapsing Universe, and it was all about stars and the death of stars and them collapsing into white dwarfs and neutron stars and pulsars and then black holes. When this book was written, it was, I don't remember the printing date, but when I was younger, and now you can tell with my beard that I'm older because I got grays, it was a while ago. And some of the science may be a little dated in it, but I remember that, talking about like the density of a neutron star and how much millions of whatever it weighs per, like a teaspoon of it. And these numbers that just were kind of astounding to me as a young kid. And that, again, that raised my awareness of just how huge of a place we live in the universe, and kind of how cool and scary it can be when you get to something like a black hole. So that book really stuck with me. And in fact, I eventually traced down, because I lost it when I was a kid, but I found a copy of it later on in life. And so I still have a copy of it. The other one is Infinity in the Mind from Rudy Ruckner. This was a book that I always thought, well, infinity is just, a number that's like uncountable. It's really big. It goes off to infinity. But this was the first book that actually made me realize there are different kinds of infinities, and different infinities have different sizes. And I had never even thought of that kind of concept. So stuff like this, again, really made me think, and captured my attention. Now, we're not going to be talking about something that maybe will be a little bit abstract as like infinities or which ones are bigger than other ones and stuff like that. That's a whole different topic. I do want to narrow it down to these are things that are finite. That's what my talk is about. But they are rather large numbers. And I got the opportunity when I was in graduate school. I went to Marquette University in Milwaukee, Wisconsin. I went there for my bachelor's and my master's in electrical engineering. So I don't have degrees in computer science. In retrospect, I probably should have, but you learn. Definitely do not regret what I did. It's just, as I got into grad school, I realized I really do like this programming thing. It actually is something that I'm interested in. And I was able to talk to a professor who had a student work on something with multiple precision arithmetic using something called the fast Fourier transform, which if you've done any engineering courses, you may have heard of. It's used typically for digital signal processing, but you can also use it to do some really cool fast math. And he wanted me to look at what you're seeing here called the number theoretic transform. So I did some research, found out about it, and did that as my thesis. And one of the things I had to do to show that all the stuff I came up with actually worked is to calculate pi. We'll get to that in a moment. So why is something like this important? And this gets into when you're doing calculations, not just with big numbers, but with any kind of calculation, you do want to try to find optimizations. You want to make sure that things are going to scale well. We always talk about you got to be in the cloud, you got to scale out, and things got to scale. But if your underlying code, if your underlying implementation doesn't scale, you can add as many functions and Kubernetes clusters and everything else. Your code is still not written to scale. Okay, and let me explain that in relation to something like just multiplying two numbers together. The way that I learned it way back in the day, and probably is still being done today, although they just use calculators and computers, but when you do it by hand, is to do this where you take the 7, you multiply it by 6, and then by 4, and then by 3, and then the 2, you shift over to the 10s, and you multiply by 6 and 4 and 3. And then you add up these columns, and you carry the numbers, and blah, 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 and you end up with the answer there. Okay. So for smaller-ish numbers, this works, and it also keeps kids in school occupied as they're doing their worksheets or whatever it is, so that the teacher gets a break. But in the real world, like especially with computers, something as small as this may not seem like a big deal, but as you get into bigger numbers, it can actually start to become a very big deal. You may have seen this thing where you're talking about big O notation, and all it really, again, I don't want to get too deep into a lot of the concepts tonight. This is more just like a breadth of discussion, but the big O notation, which honestly I don't use on a day-to-day basis. In fact, I think a lot of developers don't do that on a day-to-day basis. But it does give us a way to say, if I've got a data set or some input of size n, whatever you clarify n to being, is it n bytes, is it n lines, or whatever it is. If I start increasing n, how does that scale? How does the time or the complexity scale for a given input? When you do mathematics, especially multiplication, and you do what's called the grade school method that I showed before, it's n squared. So as the size of the biggest number becomes larger, it will actually take n squared time to finish. And on the next slide, there's actually a graph to show this. The number theoretic transform that I did, which was basically doing all this arithmetic using integers, whereas a fast Fourier transform uses doubles, so you can run into round off errors. That becomes important. Again, something I'll come to later. But this transform to do multiplication makes it go to n log n, which is better. There's actually a version of this, and even though my last name is Bock, I'm technically not German by heritage. I'm adopted, so I'm actually part Swedish, as I found out later. But I'm going to butcher this German, and I think it's Schonigstrassen. And if I said that wrong, I apologize. But this version of the algorithm is n log n log log n, which is actually even better. Okay, and this graph shows you some of these. Okay, you can see if I've got n squared, which is kind of in the pink reddish area, is worse than if I have n log n. Okay, and if I can actually do something where it's 1, if you look way at the lower right, it's 0.1. That's basically saying whatever you give me, it doesn't matter how big it is. I'm always going to give you an answer regardless of the input size of the data. So you could say, like, maybe I have some function that says you're going to give me a number that's hundreds of digits long. I'm always going to give you a 3 back. Not a very helpful algorithm, but that has a complexity of 1. Okay. Whereas, again, with these multiplications, and log n is better than n squared. Of course, if you get into something where given the input size is n, and it takes n factorial for it to finish, that's really, really bad. Okay, that's not going to scale well at all. So in these bigger calculations, you need to have efficient algorithms. Now, in my master's thesis, I was actually able to calculate pi to, the requirement he gave me was 5,000 digits. Why, I don't know, but again, computers back then, having a 50 megabyte processor was the deal. That having a 100 megabyte hard drive, whew, man, you could store a lot on that, whereas now that's nothing. But this was at least a proof to show. You can see on the upper left, you got 3, 1, 4, 1, 5, 9, 2, and so on. So I was able to do this, and I compared this to a previous result in a text file to make sure that it was actually comparing correctly. So yeah, I got this all to work. But of course, this is relatively small when you look at the records that have been made calculating the number of digits of pi. In fact, this is a slide that I had to change right before I started. It used to be 62.8 trillion digits, but then a group using Google Cloud just calculated this year 100 trillion digits of pi. Okay, because I know that's what people have been asking for, is to read a book that has 100 trillion digits. I don't even know how much that would be to print that out. That would be gargantuan. That's a lot of digits of pi. And if you remember, pi is part of figuring out things in a circle, the circumference and the radius. You see pi r squared and all that other stuff coming into play. And pi is a transcendental number. Like you saw with 3.14, whatever those numbers are, that sequence never stops. It just keeps going and going and going. And so these calculations use very advanced algorithms and computational techniques to figure out more and more numbers. And that's part of the reason why people do this, is because it's not just to say, hey, we're the winner, we've got more digits of pi than you do. It's in part to say, how could we do this in a cloud environment? How could we do this in a distributed fashion? Where are some ways that we can mathematically make this faster? Okay, and so that's part of that research opportunity to see where can we make things better. In reality, and this is a quote that I found that said, well, how many digits of pi do you realistically need? And there's a wall of text there, but the thing in bold there is what you should be focusing on, which is about 40. If you want the circumference of the universe, and you want it with the precision of a hydrogen atom, you only need 40. So that's like the most digits of pi that you need. In fact, this article does also talk about when people like at NASA or other places that make rockets and blast them off into space, how much precision do they need to do their calculations? It's nowhere even close to this. They typically use only about 15 at best of pi, because they just don't need that much precision. So calculating that much digits, it's not about, do we actually need that for anything we do realistically in the universe? It's more about what do we learn about creating programs to make them run more efficiently? And it's also kind of a nice way to test out maybe some new hardware. That's another reason you do it. If we get again into more realistic things, like just what's really in the universe, or some numbers that they're big, but they're still physically grounded. For example, what do we think the size of the universe is? And if you read things on cosmology and what we know about the universe is expanded and other things like that, this is generally a number. Of course, we can't take a tape measure and go across the universe and say, okay, that's how much it is. This is a guess, this is an estimate, but it's a grounded estimate in terms of how big we think the universe is. So about 8.8 times 10 to the 26 meters. Okay? That's quite long. That's a huge, huge amount of space. Okay? So that's a really big line across the universe. What's the smallest we could do? So there's these things that are called Planck lengths. And this starts getting into quantum mechanics, and I'm not even going to remotely try to fake it. I'm not a physicist. I don't do that in my day-to-day job. So this is more just looking up, like, what's the smallest distance? And so this is the smallest distance that you can have before things start getting really weird from a quantum mechanical perspective. And I'm just going to go, okay, I trust that. But you can see now the number is actually 1.6 times 10 to the minus 35 meters. So that's incredibly, incredibly small. And so I said, well, given the size of the universe from like one point to the other, how many Planck lengths could you fit across that line? And so that's the number I came up with. But again, this is a number that has some sense of realism to it, even though it sounds quite, it's not something that we probably have dealt with in any of the things that we build on a day-to-day basis. This does have some tie to reality, okay? We also can have a guesstimate as to how many atoms do we think are in the universe. And the number I've seen is 10 to the 80. So we have that much stuff in the universe, okay? But let's bring this down even more, not even just what's physically possible. What are some big numbers that are things that we may deal with in our lives? Though this next slide, you're probably going to laugh because it's like, there's no way this would ever happen to me. And I know it wouldn't happen to me. Who's the richest person in the world? Okay. Who do you think this is? Anybody got a guess?
Bezos?
Before, this is another slide I had to change. It was Bezos, but it's not Bezos anymore.
Is it Elon Musk now?
Yep, the guy is doing some very interesting things with Twitter. That's almost $250 billion. I can't even fathom even though that's what his wealth is estimated to be. I can't get my head around that. Okay, and I remember when I was like in college and starting my professional career, there was like this thing that went around to say how much money, because this is when Bill Gates was like building his Microsoft empire. How much money was it worth for Bill Gates to see on the street for him to actually go over, pick it up and put it in his pocket, due to how much time he was losing making the money other ways? And it was, I don't know how much it was, but it was definitely an amount that, I would have picked it up, but given the wealth that he had, it wasn't worth his time. I see a number like this and I just can't, like, what would you do with all that? I don't know, buy Twitter, I guess. So as of this moment, when I was looking it up, this is like the most that somebody has in terms of their wealth. Okay. So how many estates could this person buy of the most expensive estate in the United States? So I had to tie this a little bit to Rocket Mortgage in terms of housing and buying stuff and whatever. So I looked up what's the most expensive house or estate in the United States, and it's this one. This one is called the Chartwell Estate, and that whole area is valued at $350 million. Yeah. Again, I cannot even imagine what just the uptake of that. That's so much work. Yeah, I mean, it's like, oh yeah, maybe that looks nice, but I'm just looking at that going, God, all the dusting, that you'd have to do in that house, and of course there's the price tag. I couldn't imagine even ever buying something like that. That's way, way beyond anything I'd ever hoped to have. Okay, but I started thinking, well, what would somebody who's the richest person in the world, how many of these Chartwell estates could they buy? And so I'm going to have a little bit of fun playing with those numbers later in terms of rounding off and representing those numbers in computers. Okay. Speaking of data and computers, how much data can we accumulate with some of our calculations? So very recent history, we've had something that was very interesting to me, which is we actually took a photograph of a black hole, which when you think about it, that sounds weird because a black hole doesn't emit any light. It sucks it all in. So how can you see it? Well, you can if you use X-rays. And more to the point, you have to use these telescopes that are literally the whole diameter of the Earth. So they had all these arrays of telescopes that were picking up these signals from all different parts of the globe. And they had to synchronize their data to make sure that they were like they knew what part of the signal was coming in at a particular time. Okay. So they had these massive amounts of hard drives, even from Antarctica. They were getting signals from it and recording them. And so they had to basically bring all this data to a central place, so somewhere in Europe, and then do all this processing on this data to finally come up with a picture. And that's what you see here. This is from M87. That's the galaxy that we now know pretty much every galaxy has a black hole at the center. This one was so large that they could use it to resolve an image. And so that's what you see here. It's that the black hole in the center there, or that part of the picture, is larger than the diameter of the solar system. You could fit our solar system in that. So that's pretty big. But the number of bytes there, that's 4.5 petabytes of data that they gathered and acquired when they were doing all their measurements to create this picture. And so they ended up doing what's called a pigeon carrier network, whereas you have so much data that to try to transfer it across even like a fiber network, it's too much. You couldn't ship it from one side to another in any appreciable amount of time. They would just put it on these hard drives, and then again, they would literally ship it physically to one site and then do all the processing there, because that was far more efficient than trying to push all that data there. Okay. All right. So talked about some numbers, talked about the size of things and how do you actually represent those in computers? Okay. How do we actually put those into a computer program and do calculations with them? And what are some of the problems that we could have if we're handling numbers that big? So this is where I'm going to get into a demo of handling numbers of different representations. And again, I'm not going to get into like any IEEE standards and down into the weeds here, but this does hopefully show that you have to be cognizant and aware of the numbers that you are picking, or the data types more specifically that you are picking. Okay. So if I go to this code, so this again, all this is going to do is do some things with the amount of money that Musk has and the number of chart roll estates, and like how many could somebody buy if they had that much money. So for example, you can see here the first one, if I have a house or a property of the, and by the way, the code that I'm going to be showing here is mostly C#. And if you didn't know in C#, you can actually now put these underscores in numbers. They don't change the value of the number, but you can almost think of these as commas. So they're a way to separate out numbers so that instead of you having to see it like this, that's a little bit hard to read and say like, well, how big is that? Whereas if I can split it out like that, it's much easier to read that as 350 million. Okay. So just a tip, if you haven't seen that before in C#, I think they added that in 7, I believe. So a nice little notational thing to do. But the L at the end, also in this case, and by the name of the method, is saying that this is going to be a long. So if I zoom in here, and hopefully this doesn't mess things up too much, you can see that it's actually declared as a long data type. Okay. So a long in C# and in .NET is 64 bits. Okay. And it's a 64-bit integer. So these aren't fractions, these aren't decimals, they're just 1, 2, 3, 4, and so on. A long can be a positive or negative number. You can also have unsigned longs, which means they're only going to be positive numbers. Okay. So if that's how much money I have, or that's my salary, that'd be funny. And that's the house that I'm looking for. How many number of houses could I calculate? But I'm not just going to do it with longs. I'm also going to do it with doubles. So a double is a way to store a number, but have a fractional or decimal part to it. We're also going to use a decimal. Okay? And not just that I work in a financial company, but this is something, again, from my consulting years, working with different verticals, one of them being financials. is you find this out rather quickly that if you're going to do any type of financial calculation, you actually don't want to use a double. You want to use what's called a decimal. It allows you to get fractional parts, but it handles rounding and other calculations where you have to cut off like a fractional part of it and do it correctly in terms of how rounding is done in financial calculations. So in this case, I'm going to be doing it as a decimal, and we'll see what that result is as well. Okay. And then I'm going to do it with something called a big integer. So there is a type in .NET called big integer that's an arbitrary sized number, an integer number. Okay. So I can declare a big integer. There's no like, here it's an M, or I could say instead of var, I could have said decimal here, or something like that. There's no keyword in C# to say I want to have something as a big integer. You have to declare like this, but you can give it an initial value here, or as you can see, you can just say parse, and then I could put in the total number of atoms here as a string, and it will parse that and then give you a number that represents the size of the number of atoms. Okay. So we'll do that calculation with big integers, but then again, if you see this parse total atoms, well, what happens if I wanted to try to represent the number of atoms as a double, which is, this is kind of a notation or a syntax in C# to say it's 10 to the 80. Okay. But what happens if I really knew that the number of atoms was some arbitrary, like big fractional part number like this? What happens when I try to stuff that into a number here in C#? Okay. Then I'm also going to multiply two floating point numbers together, because I'm talking about when you are dividing numbers and when you round and you have these types of conditions in your code. Well, what happens if you're just going to add two numbers together, like 0.1 and 0.2? You look at that as a human being and you go, well, of course it's going to be 0.3. I mean, that's obvious. But as you can see by the link up there, there's a site that's giving you a hint as to the answer about what's actually going to go on. Okay, so let me stop there, because the last one I'll cover separately. Okay, but let me just run all these, make sure it will work. So we'll start as build succeeded. And if you look at these calculations again, like when I did the how many houses could I buy, it comes up with 625. But it's not because that was a perfect like division with no remainder. As you can see with the doubles and the decimals, there definitely is a fractional part. There's a remainder part to that calculation. When you do integers, you get truncation. It will just, because there is no fractional part it can hold. Same thing with a big integer. Even though you can get a big integer to hold an arbitrarily large value, it still is an integer. So you're still going to get that truncation like what you see with a long value. But you'll notice here that when I try to put in an arbitrarily long value into a double, it also has a limitation in size. And this is what I alluded to with an IEEE standard. There's standards in terms of when you're doing floating point calculations, how you store those numbers. And when you try to store anything with a decimal, even if it's just 0.1 or 0.2, you can run into a case where adding them together gives you this 0.3, bunch of zeros, and then a 4 at the end, which is usually done as a joke against JavaScript, because people, like if they're trying to make a comment about JavaScript, they'll say, oh yeah, do this in JavaScript, add 0.1 and 0.2 together and you'll get this answer. The thing though is that it's not a JavaScript specific thing. As you can see here in C#, I get the exact same problem. And it's because a decimal, or not a decimal, a number that you're trying to store with an arbitrary number of bits, because that's zeros and ones, that's what we're using on computers. It can't actually represent a 0.1 and a 0.2 perfectly. Okay. We as humans look at them and go, of course it's going to be 0.3. But to a computer, it doesn't work that way. And so you sometimes get into these kind of odd, weird cases that you have to that the results may be surprising. Okay. And again, this isn't just a JavaScript thing. It's in a bunch of languages that follow the standard. And so if you do something where the calculation was actually using decimals, then we actually do get the expected answer of 0.3. So representation of numbers, even if they're not that large, you have to be a little careful with which number or which type, I should say, you pick, not number, but type. If you're going to be doing something where you really need to count a whole bunch of things, a big integer or something that you probably want to take a look at, especially if you could run into overflow conditions. So this last one here is kind of the reverse of what I showed you before. Okay, this number is actually using what was Bezos's wealth, but it doesn't matter. It's just saying if I wanted to have 500 of those Chartwell estates, because one isn't enough, I've got to have 505 of them, and that's the cost of that estate. Well, what's the salary that I would need to do that? Yeah. Well, if you look at this number here, and it doesn't get formatted with those spaces in it, but it's 665 million, which if you think about it, that makes no sense because two of those houses cost more than this calculation. The problem is that this is overflowed, okay? Because the numbers here are ints. These are 32-bit numbers, and they can only go from basically minus 2 billion to 2 billion. If you try to go beyond those, what they do is what happens is they overflow, okay? And they basically wind all the way around to the lowest number, and then they start going up from there, okay? Because they're bounded by those two endpoints, and so they can't go beyond them. There's no way for those numbers to be represented. So the behavior is that the overflow, and what we end up here is this number, which doesn't make sense, but nothing errored. There is a way in C# where you actually can do something called a checked calculation. And in that kind of context where you use the check keyword, it would actually throw an overflow exception. Okay, I'm just not doing that here because I wanted to show when you do these calculations, if you're not careful, you can get a result that doesn't fail anything, but is obviously the wrong answer. And I'll come back to this in the slides in just a little bit. Yeah.
Hey, Jason, what's the default?
The default of
The checked exceptions or the flow?
So the default is to not throw. As you saw here, it didn't throw an exception, so it just overflows and it gives me a number back. That's the default, and the reason why is because there is a little bit of a performance hit when you do a checked calculation to a non-checked or default calculation, because now C# has to emit some assembly to say, well, if it's overflowing, then I actually have to throw a overflow exception. So there's a little bit more code. So that's why it just picks the default to not overflowing because of performance. That's primarily why it does that. But then you have to just look up the checked keyword, and then you'll see how you can put code in like a check context. And then if it overflows, then it will throw. Yep. All right. I'm going to switch real quick to these arbitrarily large calculations before we get back to overflowing again. And this piece of code is what's called, this is Russian, maybe I could be wrong, but I think it's pronounced Chodnovsky. And this is an algorithm that is used to calculate pi. I wish I would have known about this back in my master's thesis days, because even though the code, like I've got the Wikipedia link if you want to take a look at it. In fact, that's what I was looking at before I started this presentation. And I noticed right here, that's where it was reported that a new record came in this year. So I had to quickly change that slide. And yeah, there's some math here. I'm not going to go through all this, but ironically, this math here is actually not as bad as it looks, because what you can do is calculate, this is basically a summation that if you do this, this is just translated right from that page. If you do this calculation, you'll eventually converge very quickly onto a number of pi. And the more calculations you do, the more summations you do, the more precision you get. Yeah. And again, this is a very efficient algorithm to do it. It's been used for all of these records. All the records that you see here have all used this algorithm to calculate pi to more and more digits. Okay. Now, the one thing you may notice here is there's this thing called a big rational. Well, back to your math days, if you remember, if I want to calculate, or what is a rational, if I just say var x is equal to 7 divided by 3, okay, that's that's a rational. You have the numerator and you have the denominator. Yeah. There's no type called a big rational in like .NET natively. This is what somebody has created. It's from this MathNet numerics assembly. And in fact, if I go into the project here, I don't know if I have the latest one, but that you see F#, of course, but that's where this package is created. And basically a big rational has a numerator that is a big integer and a denominator that's a big integer. Yeah. But then it handles the calculations if you want to get a decimal representation of the number, sort of. The problem with this, though, in fact, if I run this code here, I'm not going to sit here and watch this because this is going to take some time to calculate in C#. The big integer has it needs some performance improvements, and because we don't have a native big rational, this has probably not been as optimized as it needs to be either. Ironically, and I am not a Python programmer, but this is that same algorithm written in Python. Okay. Now, if I go to, I should have this up already, and developers PowerShell here in Visual Studio, and I just say run Python, we'll say that, and I run it, and in about, well, it should be about a second there. So that calculates, I don't know how many thousands of digits, first 10,000 digits of pi, you can see 3, 1, 4, 1, 5, 9, 2, and so on. Okay. And this did it in about, I don't know, 4 or 5 seconds. I don't know how long it took me to do this when I was in grad school. So, it's definitely humbling to say the least. But this isn't Python. Python's an interpreted language. And yes, it has some very powerful things underneath the scenes. But compare that to me trying to do this in C#. I'm still nowhere near done. If you look at this is not 10,000 digits. You can see it's like it just stuttered there to get the next set of digits. Okay. That doesn't, I want to be really clear. This doesn't mean that C# is not, or .NET is not performant. It just means that in this area of doing large calculations, there definitely needs to be some improvement in C# because it's kind of, at least in this algorithm, it's lacking. Or I will also admit, maybe it's just my way of coding this up. I may just be doing it not in a performant way. I take PRs on my repositories, by the way. So if you want to try to make it better, I will be all ears. Okay, so it does work in C#, but I think there needs to be some improvement. There's been improvement in the math space with C#11 and .NET 7. There's this whole thing called generic math and static abstract members and interfaces that you may have heard of. That's good in terms of abstraction over mathematical calculations. It doesn't necessarily mean it makes things like big integers and related members faster per se. Okay, but the person that works on the system numerics namespace says yes, we definitely need to improve some things there. So in any event, okay, so that's just kind of a whirlwind tour of number representation and truncation and large calculations. I do want to come back though now that I'm going in my slide, unless there's again more questions. Just again, interrupt me. I'll take them as they come. But getting back to numbers that if they get too large, how do you represent them? Like the one where I took the number of houses and the cost of one of those houses. That was far bigger than an integer could hold. Well, does that really matter? Yeah, it does. In the real world, it definitely does. This is a rocket called Ariane. I think that's how you say it. And this is the Ariane 5. Okay. Very powerful rocket. We actually just had the Artemis. Is that the right name? The one that just had the unmanned capsule go beyond the moon and it's going to be coming back anytime soon. Yeah. Okay. Thank you. I want to make sure I got the name right. But this rocket had a long history of being very reliable and very performant, except in 1996 when this happened. Okay. So this is actually, I had to capture from a YouTube video a picture of this rocket going completely sideways. And that's, if you watch the video, it's actually more telling. You'll see the rocket going up, and then at some point it literally starts trying to go this way. Yeah. And as you can, what's that?
Is that where it rolled over, the numbers inverted?
Yes. So that's why I say that overflow matters, is because this rocket was trying, wait a minute, hold on. No, that's, okay, my notes and my slides, I had to make sure I got the quote right. In the article that I found that talked about what happened on this flight is the software and the hardware, and as you can imagine, these rockets, they're very customized. And they're also very optimized as well. Well, they had an overflow bug that had never occurred on any flight until this one. And as the quote says, all it took to explode that rocket less than a minute into its maiden voyage last June, scattering fiery rubble across the mangrove swamps of French Guiana, was a small computer program trying to stuff a 64-bit number into a 16-bit space. So something changed on this flight where the telemetry and the length of the flight was longer than expected, and then it actually hit this case where it was trying to store a number into a space that it couldn't. It was just too big. And so it overflowed. And what ended up happening is the rocket thought it should be going this way with its guidance system. And so it tries turning that way rather rapidly. And the stresses and the G-forces in the rocket were way, way too much, and it ended up exploding. Now, nobody was killed. This was a satellite that was being blasted into space. So fortunately, no lives lost. But this was I think it was $250 million loss in terms of not just the rocket, but also the payload. So yeah, it can definitely matter. Now, maybe we're not building systems that are launching rockets into space, but I would probably venture to guess that there are things that we're doing that maybe if we looked at it a little bit hard, maybe there is a case where we're doing something that we're overflowing and we're not handling that correctly. Those are very insidious bugs to find, and they can literally or figuratively blow up in your face. I think Lee mentioned just something real quick about cryptography. That's one that we run into all the time in our everyday lives, even though we may not see it. If you think of when you create a password, well, if you're doing things correctly, you're definitely not storing that password in plain text in a database. I hope nobody is doing that, because that is really, really wrong. You don't do that. So you at the very least are going to hash it, probably use some salt, and some other things there, but you're not going to store it in plain text. If you ever go to a site and you're like, hey, can you tell me what my password is? And they can send it to you an email in plain text and say, that's what your password is, run away. Because they should not know what your password is. They should at least have a hash of it. And so if I use SHA-512, the hash of my name is actually that big hexadecimal number that you're seeing there. Okay, so that's literally a number that represents my name as a hash. So these things exist all the time in cryptography, again, even though we don't see them. They can also exist just in some mathematical algorithms, like what we saw before with pi, but also with some conjectures. This is one that I absolutely love because it's very simple. It's called the Collatz conjecture. And this conjecture says, take any integer greater than 1 or, well, it can be 1, but 1 is where it converges, so you don't want to pick 1. But you can pick any number 1 or greater. It's got to be positive. To generate the next number, you say, if the number I have is even, I divide it by 2. That gives me the next number. If the number I have is odd, then what you do is multiply it by 3 and add 1. But that will give you an even number, so then you can just divide it by 2 right away. Okay. The conjecture states that all sequences converge to 1. And so, for example, if you look at this, if I start with 12 and you follow the arrows, you're going to see that I have an even, and then I have an odd, and then I have an even, and then, I'm sorry, I end up with another odd, then I get an even, and that converges up to 1. 1 actually goes 1, 4, 2, 1, but then you're caught in this loop. So 1 is where you converge. If I start with 16, that's very simple. You go 16, 8, 4, 2, 1. Okay. So the conjecture states that all of them are going to go to 1. And in fact, computers have actually been able to calculate up to 2 to the 68, which is some number times 10 to the 20, or just 20 digits after it. Okay, so not entirely large, but you can imagine that doing those kinds of calculations can take quite a lot of time. Okay. And you can also look at a number like that and go, wow, that actually seems like that conjecture holds. So that's probably true, right? But if you do anything in math, which that's not what I do for my job, but you do anything in math, you can't just say, well, a bunch of conditions hold, so therefore it's true, because that can bite you very easily. There is an example of something called Merton's conjecture. And this is some stuff that I found from a video on this channel on YouTube called Number File, which I would highly recommend watching. And they've got some really cool videos. They tend to keep the math pretty, I don't like using the phrase dumb it down. That's not a good phrase, but they bring it to a level that, more people that may not have a very strict mathematical background, they'll be able to pick up the gist of it. Okay. So what this conjecture shows, even if you do a lot of calculations, it doesn't mean you've proven anything. So the conjecture starts with, I've got this function that if I give it a number n, an integer, I either give a 1 back if we have an even number of prime factors, or a -1 if we have an odd number, or 0 if we have repeated primes. Okay. Why somebody comes up with this, I don't know. You're bored on a Saturday night. You're like, hey, let's just come up with this sequence. Okay. So here's some examples of numbers n, and then what the result of the calculation is using that function. Okay. Doesn't really matter how we come up with these. That's just how this algorithm works. Okay. The next part, though, is the actual conjecture. The conjecture says this: if we take that function that says, given a number, is it going to be 1, -1, or 0? And then we go from like 1 to that number and add up all those 1s, -1s, and 0s, we're going to get another result. That's called Merton's function. And the conjecture says that it's bounded by the square root of n. Okay. So just to give you an example real quick, to do Merton's function with 7, you get a -2 out of it because you're adding up all those numbers. Okay. And if you plot this out for the first 10,000 values, you see it kind of bounces up and down as the numbers change, but it's bounded by this square root of n. That's what that parabola is on the graph. Okay. And so it looks like, well, at least up to 10,000, we get nowhere near close to it. It seems like this conjecture holds. But it was actually discovered that somewhere around 10 to the 10 to the 40, it will fail. That bouncing result eventually will cross that square root of n line. Yeah. So you can't just assume that if you've done enough calculations, even if they're really big numbers, that proves something. And then that's why when you start getting into some very advanced mathematics, I just gloss over and go play a video game, because one day I said, well, I know Fermat's last theorem, if you remember that one. That was proven years ago. And I said, what does the actual proof look like? And I found it somewhere online, and I tried to look through the first page of it, and I said, nope, none of it made any sense. It was just so far beyond any of the training I've ever had in math, stuff that I've never even heard of. But it's been accepted as a proof of that. So you would need to do something like that for the Collatz conjecture. And like this one is showing the Merton's conjecture. You can find a number, even though that's a really, really big number. So now it's 10 to the 40. So that's one with 40 zeros after it. But then you raise 10 to that number. That's a huge, huge number. Yeah. But we're not done there. I'm going to end this talk by going into some big numbers that are just ridiculously huge. These are ones that you would never have to worry about overflowing, because you could build the biggest system in the cloud and it would have no chance of storing these numbers. Okay, so this is going to go a little bit over the deep edge. There's two numbers that I'm going to talk about. This first one is called Graham's number. And you can just kind of gloss over that definition of where Graham's number comes from. But it has to do with dimensional hypercubes, blah, blah, blah. But the last question there is basically saying, what's the smallest value of n where it satisfies this condition, whatever it is, okay? And they actually found that there was a smallest value of n for this, okay? And that value is somewhere between 6 and g of 64, okay? So it's a finite number. But what is g64? So we got to kind of give some notation here to give you some sense of scale about how big this number is going to get. And Lee, I hope you don't have to get into this with your day job, but do some notation here. So Donald Knuth, which I'm sure you might have at least heard the name, somebody who's very, very influential in computer science, has the Art of Computer Programming books that people put on their shelves and never read, like me. But he's done a lot for computer science and computer programming. He came up with this notation, this arrow notation. So if you say 3 arrow 3, that basically means 3 to the power of 3 or 27. Okay, so far so good. If I do 3 arrow arrow 3, that's how that number is calculated. Okay, so as you can see, just by adding 1 arrow, we now have a 7.6 trillion number. It's increased rather rapidly. If I did 3 arrow 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 3, I can't even put that on my screen. Like, I don't even know how to show you how big that is. That's gargantuan. Yeah. But oh, we're not done yet. We're not even close. Yeah. As a side note, you can also do this notation where instead of putting all the arrows in there, you can just put an N there, and that means how many arrows you really are trying to show. Okay, so just keep that in mind as well. So now let's go back to Graham's number. This again is this number that when you're doing this coplanar coloring thing, whatever, that it's the upper bound. Somewhere from 6 to it, there's a number in there where it shows, yes, that condition is satisfied. So this is G of 1. Okay, this is our starting point. This is 3, 4 arrows, 3, which is even bigger than the gargantuan number I just gave you. G2 is 3 of G1 arrows of 3. Okay, so this has gone well beyond anything I could imagine. But that's just recursively done to get to G64. Okay, and that's what that number is. So this is a finite number. This is not this is not an infinity of any sort. This is a literal number. But you can also think of it as this kind of calculation. We have all those layers of all those 3s with all those arrows. It's, again, I can't come up with a name or a word to describe how big this number is. And yet it is a finite number. The funny thing is, if you think about it, you can actually calculate the end digits of the number rather easily. Well, easily-ish. Because if you don't care about all the things that are being multiplied on at the bigger parts of the number, you just keep the end part of it. And so you can actually calculate the last 500 digits of Graham's number. And that's what this is right here. Okay. So we know what the last 500 digits are. We don't know what the whole number is. Okay. So, but that's not the end of it. Because there's another number that is finite, but that puts Graham's number to shame. And it's called tree of 3. Okay, so what is tree of 3? This you can think of as trying to do graphs with seeds, okay, and building unique graphs with different colored seeds. Again, there's a lot of deep mathematics here, but at the end of the day, you're basically trying to say, if I have 1 colored seeds, 2 colors of seeds, 3, and so on, how many unique trees can I build without repeating what I've done before? Okay, so here's the first 3. So again, I have a bunch of seeds that are all colored red. And then I have a bunch of seeds that are colored red and blue. I'm sorry, green. And then red, green, and black. The colors don't matter. It's just trying to differentiate them. Yeah. And so what this tree function is saying is how many unique trees can you build with these seed combinations without repeating or including a previous one. Okay. So tree 1 is really simple because there's only one option. If I tried to build another tree that has 2 green seeds in it, well, I'm repeating one of those. So this is the only unique one I can make. Okay. So tree of 1 is 1. Tree of 2, you can only do 3 unique ones. If you try to make a 4th, you're going to include what you've done previously. So a tree of 2 is 3. So far, this doesn't sound too bad. Yeah. Tree of 3. Well, I can start doing this. And then you see that ellipses there. Yeah. That ellipses is carrying a lot of weight because what actually is the end of tree 3? How big is this? Graham's number can't hold a candle to this. It is, again, a finite number, but it's a number that we can't even figure out what the end digits are. All we know is that mathematically it is finite. That's it. So if you looked at the big O notation for this, I mean, it's probably just the line at the left. That's it. Because it just skyrockets really, really fast. So hopefully we don't get into those in our everyday calculations, but this does show you that you can have some numbers that aren't infinite, but are just massive. Okay. So again, this talk was meant to be fun. It's not a talk that's necessarily you're going to try to calculate Graham's number when you get back to your computer. Well, you might try to calculate the last 1,000 digits of it or something like that. But it's more to kind of make you think and inspect on things that you are doing in your lives. Not just in learning maybe a little bit more about large precision calculations, or if I do have large numbers and things that I'm working with, to learn a little bit more about how these are calculated efficiently. But it's also about looking at the calculations you're doing in your programs and thinking, maybe I don't have enough storage with what I'm doing. Maybe I am doing things that are causing overflows. Maybe I do have cases where we may need to use a data type that won't make us run into a condition where we have an overflow, because they're not going to cause your code to fail unless you do it in a checked in C#, but they can cause some really, really bad bugs. So this is also a case where I'm saying to people, go look at your code, see if there's potentially areas where you may need to change the data types you're using. Okay. So hopefully you've had some fun with me doing this talk, learned a thing or three, and hopefully I've entertained you to some degree. So that's all I have. Any questions, comments, anything at all?
I understood some of that.
Okay. Well, that's good. So, did that help, Lee, or was, with what you're doing, or did it have any relevance to what you're working on, or?
Not directly, but it was fun. It was also nice to see that you're seeing the same performance problems with big number calculations that we were seeing. So that's kind of encouraging. The .NET team is aware of this, and because of the project that I'm on is actually Microsoft, they've put in a word with the .NET team in C# 12 or 13 or whatever to improve the performance of the calculations of the big numbers. So
Okay. Have you run into somebody named Tanner?
I have.
Okay, because I think his name is Tanner Gooding. He's basically the head of system numerics, and he was deeply involved in the whole generic math implementation in C# 11. So maybe we can talk later, but that's a person that would love to get feedback from you. I know you already said that you've been talking to Microsoft about it, but he is the person that's the head of that area. So maybe somebody to try to talk to directly, because and I know he said he really wants to get customer feedback on this, because part of the problem, people look at big companies, especially like Microsoft, and they're like, oh, well, they make billions of dollars. They must have an infinite number of people to get stuff done. And it's like, no, it's like any place, they have finite resources, and they have a finite number of people and a finite amount of hours. And, they can only work on so much. And so they have to say, well, we know that we'd like to improve this area, like system numerics, but we also have to do these other things. So which one matters? And part of that comes to, what's our customer saying? What's the feedback they're giving us? And so, not that you want to be a squeaky wheel, but you kind of want to be. If this is something that's important to what you're doing, then if you're saying, hey, we're using C#, we're using .NET, and we're finding out that this is kind of slow, or we've looked at other languages and it works faster, that can raise their attention. So something to keep in mind.
Surprisingly, JavaScript actually has big number support for modern browsers, and it has actually a pretty fast performance for doing power modulo operations in big browsers, which is what we needed to do. And that was kind of surprising.
Even like Python itself, when I was showing it, the calculation, like you saw, it doesn't take that long for it to finish even in Python. It's because most of the libraries and modules and things underneath the scenes are highly optimized. So while the language itself is arguably interpreted, once it's going to do these calculations that are actually quite large, that's in a native space. So they can get away with doing some stuff pretty fast. Funnily enough, there's another guy on YouTube. His name is Matt Parker, and he has a channel on YouTube called Stand Up Maths. Really good. It's really interesting to watch. Again, it's not really deep into math. He tries to be a little bit more entertaining. And if you played Wordle, I don't know if you've heard of that game.
Reminded me I didn't play my word today.
Oh,
Right.
You better do that. You're gonna run out of time.
I do that too.
I learned about it from you.
So my actual what are my stats right now? Because like there'll be a day where I'll forget and I'm like, damn it, my streak's over. So I currently have a 77 streak. And if you don't know what I'm talking about, it's this thing where you have to guess a 5-letter word in 6 tries. Okay, so as you pick letters, it will tell you if it's in the right position or it's a letter in the word, but it's not in the right position. And so then you got to figure out what it is. He did something that wasn't Wordle specific, but what he said is, how many unique combinations can you get out of the alphabet for a 5-letter word? And you can actually find 5-letter words. Some of them are really strange and I've never even heard about before, but that don't repeat letters. They're all unique. So there's like 25 letters altogether from those 5 words. And how many of those can you find? And so he wrote a program, getting back to Python, because he loves Python. Like he said, he's not a developer. He's more of a mathematician, so he'll use Python just to do stuff. And so he wrote something to do a brute force search. And he said it took his program a month to come up with the answers. What do you think the internet did? Well, developers, they're going to see something like that. They're going to see it as a challenge, not kind of a challenge. They're going to go, oh, I can do that better. I can do that faster. And so there started to be a fast-growing competition to see how much better could they do this. And people switched to different languages like C++ and Rust. And it's funny because it got down to from a month from his original program to literally a millisecond if you optimize it. And he talks about in a subsequent video about like what people were doing to optimize the searches, and it's quite interesting. But yeah, the languages themselves, if you have the tools underneath the scenes to do optimizations, and also are you coding it correctly? Because like he explains, if you encode what you're trying to do in an efficient way, basically, if you think about the alphabet being 26 bits, you can do some really efficient coding things that way. So it's also about how the stuff is represented. It can really make a difference. So interesting. I find that stuff to be interesting.
I had a question about performance. I'm actually, I've gotten into bijective functions. For example, I'm sure you're familiar with Cantor's pairing function, which you give it an integer and it maps the set of all integers to the set of all pairs of integers. Right.
Don't assume that I would know it.
Right.
Pairing function?
Yeah. It's so when you talk about like yeah, well that diagram sort of illustrates the idea is basically he showed you that you could map the set of integers to the set of rational numbers with this sort of like diagonalization. You can kind of see how you start from 0 and then you go to 1, and you're basically kind of traversing the grid. But you can imagine like maybe the numerator is goes up and the denominator goes down, or sorry, goes towards the right. And so he showed that integers and rational numbers are isomorphic in a way. You can always correlate each. But I've been getting into that a little bit, and I've come across some papers, and I've played a little bit with trying to get some performance out of it. But I was wondering, like, especially when it comes to doing things like taking like nth roots. I mean, do you have any recommendations for like any libraries that are good for I guess specifically big integers? I actually kind of don't need the floating part so much as was it the MathNet? Is that what you have your best experience with?
Well, best experience in terms of just using it here, but let me do this. NuGet, search for that, and they're up to 5.0. I should update my stuff. Maybe it'll be faster now. I don't know. Here's the site. So let me post that in the chat just so. Actually, that I wanted to post it as text, paste as plain text. There you go. Okay. Thank you, Microsoft. It's like I always wanted to just post as plain text, and I know you can do it in a different way. Anyway, this would probably be the best place. Again, if you're in the .NET world, and you want to do more mathy things, for lack of a better term, this would be the place that I would go and look. Okay. It may not have what you're looking for, but it might. But this is where I would start. Okay.
And just to give you like one other thing, I don't know if you're interested in this, but I sort of discovered like a few years back that you can take that Cantor pairing function, and there's a bunch of other pairing functions, and you can kind of turn it on itself recursively, and you can use it to effectively count things that aren't numbers. Like you could come up with like an abstract syntax tree, like a recursive definition of a language, and then you can sort of completely count everything, or in other words, you can map any expression to an arbitrary number and back and forth, but it's complete, and you get this quality of not having duplicates, like you know. So essentially, you can kind of enumerate stuff.
Okay.
But you know, if you're trying to encode like a big expression, you need big numbers. So
Yeah. Okay.
I appreciate it.
Sure. Yeah, and again, the stuff that I do with not just my day-to-day job, but other things, it's actually not very mathematically intensive. So that was a lot from my, all the way through graduate school. And it's kind of sad because then once I got out of school and got into the quote unquote real world, it became like more like business applications. So that's kind of why I like doing this talk, because it gives me a chance to at least play with some of this stuff again.
Thank you. Appreciate it.
Yeah, you're welcome. If there isn't anything else, Lee, I think then we're done.
So when done. Well, thank you so much for joining us tonight. Really appreciate it.
Thank you. Appreciate it.
I have you up for some esoteric language. Maybe if I can convince people that's a good talk.
Okay.
All right. Enjoy your snow. Have a good
All
evening.
right.